we were just talking about how all these different methods in machine learning arise naturally from the problem of trying to minimize the expected loss for in thinking about decision theory. And we were doing this in the context of, in particular, supervised learning, where we wanted to predict some value for a y, a class, or a target variable in the case of regression, for a particular value x given our data. But in fact, all these methods are much more general. This similar type of problem arises in a more general setting, and all of these methods are also applicable much more generally than just in supervised learning. So to give you an example to illustrate this, let's take a look at the problem of density estimation. So density estimation is an unsupervised, you might say an unsupervised technique. And what is density estimation? So in density estimation, again, we get some data, but this time we just get x's. We just get some numbers, x1 through, or rather some vectors, typically, x1 through xn, some data points, and each of them is in, it's typically a high dimensional vector, let's say in RD. And now we're going to assume that these are random variables, x1 through xn, and that each of them has some, so we're going to assume that they're IID. So they all have some common distribution. And for now, let's assume that it's a density. That's typically the case that one would consider. But you could also do a more general type of estimation of a distribution for these x's. And now the problem, the goal, what do we want to do? We want to estimate, well, we want to estimate the density of these things. So if these were distributed according to some distribution P, then we would estimate the distribution. And we're going to think about this from a probabilistic perspective. Well, these are random variables, so that, I mean, there's a bunch of ways that one can approach density estimation. Some very common ways would be, well, the simplest would be like a histogram. You know, say these were 1D, we got some points, and you make a histogram, typical thing. That's maybe the simplest. Another approach which is common is kernel density estimation, where you put a little kernel on each point. If I get all these points, I put some kernel on them, and I add all the kernels up, and I get it. So that's like a kernel density estimation. But let's think about this from a sort of more probabilistic approach. And remember before, when we were talking about supervised learning, we talked about introducing these parameters to parameterize the set of distributions that we were going to consider on the x's and y's for the joint distribution. And now let's do the same thing. Since that was useful, let's do the same thing. So we'll have parameters, theta, parameterizing a distribution on these x's. So let's call it p theta. And now we will think about these parameters as also being random variables. So we'll think about theta as being random. And we will think about the following process. Say, so we're going to suppose that this data is generated from a model in the following way. First, so these thetas are random, so they have some distribution, say whatever it is. So you're going to pick a theta from that distribution. I'll draw it in this way. And then, using that theta, you're going to draw x1 from p theta, and x2 from p theta, and so on, up to xn. And each of them, I'm drawing it this way to sort of suggest that they are independent draws using this same theta. Independent draws from this distribution. So if we write down some probabilities now, what does this mean? Estimate the distribution. In this context, what that means is we want to compute the following value. We want to compute the distribution on a new point, x, given all of our old data. That's essentially what this means in this sort of context. We want to estimate the distribution given what we know. So we're given this data and we're estimating the distribution. And what is this? Well, we have these parameters, so let's use them. So let's how can we introduce the parameters? Well, we can always introduce them here and integrate over them. So that we can do. And now this is looking a lot like before in the supervised setup. Remember we had this thing, except now the x is on the other side and there's no y. And we remember we conditioned on the theta, so let's do that again. So let's write this as p of x given theta and d times p of theta given d theta. And now, so this part, by our assumptions on, so this, to make this, I should spend more time to explain this part, but it turns out that under this type of model, you can just trust me on this for now, that we can get rid of this d. This is not particularly important for what I'm about to say, but it's true. So we can get rid of that. And now we have the following setup. So we have this thing is equal to that. And so this part here, once again, is this part is the posterior distribution on theta given our data. That's what it's called. And you might say that you might call this a predictive distribution as well on the x's given the data. And now we have essentially the same problem. So let me make some more room here. This part is very nice. This is nice because that's just how we, this is just this is just how we define the distribution on the x's. This is basically, that's essentially what this is here. So p theta of x, I used that notation before, but when we think about theta as random, then we should probably write it this way. So that we have, we are assuming that we know exactly what the form of this expression is under our model. So that's by assumption of a nice expression. This part can be nasty. This could be nasty. And once again, this integral can be nasty. So we have, for the unsupervised problem, for this density estimation problem, where we're trying to estimate the density of x given our data, we run into a very, very similar problem as in the supervised case. And as a result, all those methods which I mentioned before can be applied in just the same way to this type of problem as well. So this was a little, another example to illustrate how this arises, but even more generally, many types of problems when you have a a family of distributions which have some parameters, and you think about those parameters as being random, then you integrate them out and you get this nasty sort of integral or sum, and this posterior distribution, which can be nasty. Sometimes it's not. Sometimes it's nice if you assume a nice distribution, but for a lot of more complicated distributions, this part's nasty and the integral's nasty, and you have to resort to some approximations, and that's where these methods come in. Well, at least the approximation methods. So hopefully that gives you a sense of how these methods apply more generally as well.